shadow eclipses the face of a star. Darkness falls where once there was light, leaving only the faint trace of the solar corona. Deep inside the star's core, gravitational pressures raise the temperatures so high that ions of hydrogen are fused together to form ions of helium, releasing vast amounts of energy. This energy forms a heliosphere, a zone of solar influence in which the solar wind and its magnetic field dominate interstellar space. How far this star's heliosphere actually extends is not known. Perhaps 7,500 million kilometers, maybe up to 15,000 million kilometers. The star shakes and vibrates as it furiously resists the forces of its own gravitational mass. It has engaged in this titanic struggle since it was first formed, more than 4.5 billion years ago. Eventually it will lose, ballooning outward to become a red giant and consuming all before it. One day it will shrink again, ending its days as a tiny, burnt-out stellar remnant, known as a white dwarf. This is no ordinary star. This is our sun. It is the only star that we have any direct knowledge of. It is 150 million kilometers from the Earth, measures 1.4 million kilometers across, and releases in 1 second as much energy as the United States of America would use in 30,000 years. It is the reason that life exists on Earth, and even the slightest variations in its output of energy can have the most profound effect on our planet. The Sun is orbited by the Earth every 365 days, an Earth year. But this orbit takes place within what scientists call the ecliptic plane. This can be thought of as a huge disk on which the Sun and its planets rotate. Because we've only ever been able to view the Sun from the ecliptic plane, or very near to it, we have only really studied the Sun in 2 dimensions. To see it in 3 dimensions, it is necessary to leave the ecliptic plane completely and travel around the Sun's polar regions. This is exactly what the deep space probe Ulysses will do. It has been built by the European Space Agency as part of a contribution to an ESA NASA cooperative project. To leave the ecliptic plane, Ulysses needs a huge amount of energy. To provide this, ESA and NASA engineers decided to use the gravitational pull of the awesome planet Jupiter as a slingshot. To get to Jupiter, the planetary alignment with the Earth has to be correct. That happens about every 13 months. The next available window for launch is between the 5th and the 23rd of October 1990. Any spacecraft, and Ulysses is no exception, is subjected to extensive testing. It is vibrated, subjected to acoustic shocks, heated, cooled, spun, despun, and tested for magnetic features. Ulysses is a joint ESA NASA mission designed to be launched by the Space Shuttle with an upper stage booster consisting of an inertial upper stage and a PAM-S, which together inject it into its interplanetary trajectory. Ulysses is a spin-stabilized spacecraft containing 9 different sets of scientific instruments. It contains 2 onboard data recorders so that scientific information can be stored and transmitted later. Communications are via a large high-gain parabolic antenna, and a radioisotopic thermoelectric generator provides power. Ulysses cannot use solar power because its mission is too long and the spacecraft travels too far from the sun. Ulysses will be launched by the American Space Shuttle Discovery. After launch, the shuttle enters an orbit 296 kilometers above the Earth. The shuttle is designed to place spacecraft into orbit around the Earth, and so cannot send Ulysses on its journey to Jupiter. To do this, an upper stage consisting of an inertial upper stage, or IUS, and a second rocket called a Payload Assist Module, or PAM, are used. Gently, the entire assembly is elevated out of the shuttle's payload bay. When it is angled at 58 degrees, a spring release system pushes it away from the shuttle. The shuttle now backs off, its mission completed. Ulysses and its upper stage are on their own. The IUS contains its own navigation system, which now has to get Ulysses into the right orientation to begin its journey to Jupiter, whilst at the same time protecting its precious spacecraft. It turns tail towards the sun and starts to roll the whole assembly slowly so as not to overheat Ulysses. When the IUS computers have decided that the rocket is correctly oriented for the start of the interplanetary voyage to Jupiter, the rolling is stopped, and the first of its 2 motors are ignited. Ulysses surges away from the Earth, picking up speed until the first stage is burnt out. Coasting for a short while, and then igniting the second stage. The IUS computers check the velocity and orientation, and when they are satisfied, the second stage is discarded. The PAM now takes over. First, it spins Ulysses to 70 revolutions per minute to increase its inherent stability. It then discards the spin motor assembly and fires a Star 48 motor to gain sufficient energy to reach Jupiter and swing around the planet. After burnout of the Star 48, it has to de-spin Ulysses to 7 revolutions per minute. As an ice skater extends her arms to slow down, so the PAM throws out weights on the ends of lines. These absorb energy and slow the spacecraft to 7 revolutions per minute. The PAM is then discarded, automatically switching on spacecraft radio transmitters to NASA's Deep Space Network tracking stations. Ulysses is en route to Jupiter. Well, almost. Through the Deep Space Network, ESA's team members now have control and take steps to protect Ulysses thermally by making sure that it is spinning approximately at right angles to the sun. They also make small corrections to the original injection orbit, which may not have placed it with complete accuracy on course to Jupiter. One by one, the Ulysses payload of scientific experiments are switched on, and a radio boom containing gamma ray and magnetic sensors is deployed, together with an axial and 2 wire booms. Some 50 days after its launch, Ulysses has become what it was designed to be, a fully operational scientific research instrument, collecting data all the time as it travels through space. Jupiter is one of the most majestic planets in the solar system. It is also the largest. In its atmosphere, a huge 300-year-old storm rages, whilst smaller cyclonic regions of turbulence create the exquisite bands of color that characterize the giant planet. It is 318 times the size of the Earth, orbited by 16 moons, and is about 778 million kilometers from the sun. It has a very strong magnetic field and is surrounded by formidable belts of radiation. But one of its oddest features is the speed of its rotation. Jupiter turns once every 10 hours, and this extraordinary speed is probably a factor in determining the strength of its magnetic field. To provide more data on these effects, Ulysses will make detailed measurements of the magnetosphere of Jupiter as it flies by. 485 days after its launch, Ulysses begins its entry into the Jovian system. It is traveling in a trajectory 30 degrees north of Jupiter's equator. Some 12 hours after it begins its entry, the gravitational grip of Jupiter tightens on the tiny ESA spacecraft. Ulysses begins its sudden descent, sweeping across the darkened equator at a distance of about 450,000 kilometers. As it passes the southern pole of Jupiter, Ulysses has begun its long journey towards its end objective. Gradually, the great planet fades into the distance as Ulysses speeds out of the ecliptic plane and into the uncharted regions of the heliosphere. This is what scientists have been waiting for. But what exactly is their interest in the sun? To begin with, Ulysses will use Jupiter and the sun to conduct a curious experiment. As it leaves Jupiter, the spacecraft will come into a position in relation to the sun at which background noise is minimal. It will use this opportunity to search for elusive gravitational waves. Theoretically, it may be possible to detect these by measuring minute radio perturbations. Although not a primary part of the Ulysses mission, the discovery of gravitational waves would be a breakthrough for physics. They should exist, largely because Albert Einstein predicted them as part of the universe of relativity. The theory says that time and space can be thought of as a sort of fluid grid, the lines representing distance as a measurement of the speed of light. An exploding star, or star which collapses into a black hole, would have the same effect as dropping a stone into a still, calm pond. Ripples of gravitational energy, gravitational waves, should spread outward and should be detectable. But Ulysses' real objective is the sun. The sun completely dominates the solar system and every single aspect of our lives. Although not large by the standards of other stars, it dwarfs our world. This is our planet. This is Jupiter, the largest planet in the solar system. And this is the two on the same scale. But this is the Sun on the same scale. Exactly how the interior of the Sun works is not really well understood. Deep inside the core, gravitational pressures raise the temperatures so high that ions of hydrogen are fused together to form helium, nuclear fusion. This releases energy and is the source of the Sun's heat. However, Ulysses is not designed to provide any direct information about the internal solar processes. Rather, it is concerned with the external environment and the influence of the Sun, the heliosphere. In this respect, the heliosphere can be thought of as a huge system driven by the energy of the Sun. The function of Ulysses is to map this system. What might this map consist of by the end of the mission in 1995? The scientific key to the Ulysses mission is the corona of the Sun. The Sun's external regions are divided into a photosphere, a chromosphere, and finally the corona. It radiates outwards in vast streamers, forming curious plumes around the equatorial zones. From time to time, coronal holes appear at the open polar zones. On other occasions, loops form, which are associated with solar flares, but these appear to be confined to the Sun's equator. The loops set up local magnetic fields or closed loops. The corona consists of plasma or ionized gases with temperatures about 1 million degrees Kelvin. This itself is odd. The temperature of the photosphere beneath the corona is much cooler. Either our basic laws of physics are wrong, which is highly improbable, or there is a heat generation and heat flow mechanism between the two that is not understood at present. The complicated, erratic, and highly energetic structure of the corona produces the solar wind, a stream of plasma flowing through the solar system. The solar wind can be easily observed in high northern or southern latitudes of the Earth as it becomes trapped by the Earth's magnetic field. The result is a spectacular display known as the aurora borealis. But the solar wind is also very chaotic. Although it radiates outwards, its flow is not constant. There are storms and gales, periods of comparative calm and quiet. Finally, the Sun acts like an enormous dynamo. Its external region rotates every 27 days, whilst its internal layers rotate more quickly. This generates a magnetic field, but the field itself is curious. Overall, it is quite weak, only about twice that of the Earth. However, around sunspots, the magnetic intensity increases by a factor of 3,000. Why is not really known. The development of sunspots follows a particular 11-year cycle. At sunspot maximum, large solar flares occur that cause intense magnetic storms on Earth, affecting communications. As the Sun is also rotating, fast and slow streams of the solar wind can collide, creating confusion. But this view is what we see from within the ecliptic plane. How it behaves at the poles is one of the primary reasons for building Ulysses. It is probably very different. Yet for reasons again not well understood, the polarity of the Sun flips every 11 years. The North Pole becomes the South Pole and vice versa. A change in solar polarity is expected during the Ulysses mission. The magnetic field lines are drawn out by the solar wind, but at the same time they are able to memorize their position. They act as a conduit for exotic cosmic ray particles which are drawn towards the sun along field lines. Near the ecliptic plane, the journey along the wound-up, tangled field lines changes the nature of the cosmic ray particles, nuclei of matter probably originating from a supernova explosion. However, over the polar regions, the field line structure is probably much less chaotic, and such particles should be detectable in their original state by Ulysses, working outside the ecliptic plane. To study all these phenomena, Ulysses has 9 sets of scientific instruments and a very long way to go. About 120 investigators, representing 44 research institutes in 12 different countries, will use these instruments to investigate the corona, the magnetic field, the solar wind, plasma waves, solar radio noise, solar X-rays, energetic particles, cosmic rays, cosmic dust, interstellar gas, and gamma ray bursts. Now, if we can imagine all these solar features assembled together in a computer model, Ulysses' view of the sun would look something like this. In June 1994, 4 years after launch, it will approach the southern polar zone of the sun. It will cross this zone over a period of 5 months. By February 1995, it will cross the ecliptic plane and the equatorial zone of the sun. By June 1995, it will then begin its passage across the northern polar zone, completing this by the end of September. Even by that stage, our view of the sun may well have changed quite fundamentally. To understand the sun better, we can see that we have to observe it in 3 dimensions. But is it important that we obtain a better understanding of the sun's heliosphere? It is probably essential. Small changes in the output of energy from the sun have a profound and complex influence on our world. 3.5 billion years ago, our planet looked like something from Dante's Inferno, a violent, primeval, methane-dominated world. But profound chemical changes were probably taking place even at this early stage under the influence of the sun. 3 billion years later, the Earth had been transformed. It was chemically different, and complex organic molecules in the form of life were well established. Yet it was still a very strange planet. Even 50,000 years ago, it still looked very different, covered in enormous sheets of ice. A downturn in the output of solar energy is considered to be the most likely explanation of these ice ages. These variations, often very minute, continue today. The evolution of the Earth and its myriad of life forms have all been dominated by the sun and its little understood energy cycles in one way or another. Partly as a consequence of this, whole species of life have come and gone. Lush, fertile valleys have become sand-strewn deserts. The history of the Earth is one of constant change, and in all of this the sun is a key player. We need to understand better how it works. We need to learn more about the heliosphere because we live inside it, and we need to know more about complex solar cycles. Exploring the 3rd dimension of the sun's environment will contribute substantially to knowledge of this star and other stars. That matters. Our future is entirely dependent upon the sun.